All right, so today we're shifting to a new function. This is good stuff. We're gonna start moving towards quadratic functions. So we're gonna start with graphs of quadratic functions. It's gonna be related here soon, not today necessarily, but coming up very shortly. We're gonna relate the graphs of quadratic functions to the stuff we've been doing with transformations, right? If you think back to what we've been doing with the absolute value graphs, we came up with a vertex form of an absolute value graph, right? Should we review one of those, how to graph an absolute? How are we doing on that? Do we want to go through an example, or are you feeling good about that? Give me I need just a quick check here. Give me a 5 fingers if you're feeling really good about graphing absolute value functions. Give me 1 if you feel terrible, or somewhere in between. Oh, wow, we're looking, okay, this is good. That's pretty good, that's pretty good, okay. Okay, and what's that, that's like, kind of like that or something? Okay, all right. Okay, so we're pretty good then. So we're going to eventually, and I just want you to see where we're going with this. I think that's really helpful in math to kind of have a roadmap where you're heading. And we're going to eventually be able to say something like this. We're going to be able to say if we've got some parent graph, and we even talked a little bit about this the other day. If our parent graph is x squared, right, and we're going to talk about graphs of parabolas today, then we're going to be able to do something like f of x equals, negative 2/3 times x plus 1 squared minus 4. And what do you think we did to that parabola graph? You can probably already tell me, to the parent graph.
We subtracted 3.
Okay, so one at a time, raise hands, how about? Help me out here, somebody. Help me out with one thing. Yes, ma'am.
We moved it 1 to the left.
We moved it 1 to the left. Okay, somebody else, give me something else we did. Yes, sir. We flipped it upside down. What else? We moved it down 4. Very good. What else? What did we do?
What does this do?
The squared, that's just part of the squared is part of the parent graph, right? So the squared is going to make it, instead of it being a V, it's going to make it a U. It's going to make it a parabola, right? Okay, but what else? What did the 2/3 do? It's going to squish it a little bit, isn't it? It's going to vertically compress it by a factor of 2/3. So all of the y values are only going to be 2/3 as far above the vertex as they were previously after we squish it, right? Okay, but that's coming up, right? We'll focus on that. We'll come up with a vertex form for parabolas, but not today. Today we're going to talk about a different thing. Today we're going to talk about standard form of a quadratic function. And I know maybe what you're thinking here. We saw this a little bit with lines. We'll see it even more with other functions. Why do we have so darn many different forms of these things? Because they all do serve different purposes for us, right? Sometimes it's useful if we're trying to graph a function. Vertex form is typically the best way to write it, right? For example, we'll see that when we graph parabolas, you're going to really like graphing parabolas in vertex form the best because it's so easy to do, right? It's very simple. But for other reasons, we might want to graph a function in quadratic form. For example, if we were going to be solving systems, it'd be nice to be able to put them in a standard form. We can line up all the x squared terms and the x terms and the constants, right? You kind of have a sense of that, right? Okay, so standard form, well, you don't know what it is yet, so I guess you don't have a sense of that. Standard form of a quadratic function is this: ax squared plus bx plus c. So what we're doing here is we're writing it, what we're eventually going to call that is we're writing that as a polynomial, where we're separating all of the terms, the x squared term and the x term and the constant. And they each have their own meanings when we write it this way as well, but it would have a little different context. And then eventually we'll even look at these in what's called a factored form, okay, which is useful for another reason that we'll get to, we'll talk about when we get there. But each of these different forms, there's a reason for it. So it's not just to make things difficult for you. So we already know that a quadratic function, or if I graph a quadratic equation, I'm going to get a U-shaped curve called a parabola. There's an example of one, right? So if A is positive, then remember that means that it's been either stretched or compressed, but it still opens up, doesn't it, right? If A is negative, it's been reflected vertically, so it's opening down. You can still stretch or compress it though, right? So that's a good thing to associate with this. Positive A opens up, negative A opens down. So if we want to talk about the anatomy then of a parabola, what are the parts that we're interested in on a parabola? We've got the line of symmetry we've talked a little bit about, right? That's that even symmetry that we spent a little time talking about, about a week and a half ago. The line of symmetry is just that vertical line passing through the parabola that it's the line that's going to allow us to reflect the parabola onto itself. So imagine this. Imagine if I were to draw the parabola, half of it in wet ink on a piece of paper, and then I fold the parabola around the line of symmetry, the wet ink would create an imprint of the other side, right? You know what I'm talking about. So the line of symmetry is the line of folding for the parabola. The axis of symmetry, we call it, so let's label that. Here's our axis of symmetry, right there. The formula for the axis of symmetry is x equals negative b over 2a. Okay? What are the a and the b referring to? They're referring to the coefficients of x squared and x. When we write the parabola write the function in standard form, we're writing it with the parameters a and b and c. Just like when we wrote lines, the parameters we used were m and b, right? We said y equals mx plus b. And so by dialing in values of m and b, we could create any line. In the same way, if I dial in values of a and b and c, I can create any possible parabola, right? How come we need 3 instead of 2? Because a parabola is a little bit more complicated, right? A line's pretty simple. All a line needs, the line always has the same shape. It's just how are we going to tilt it, right? So what's its slope and where does it pass through the y-axis? Parabolas are more complicated because they're not straight, right? Parabolas are bent and they're curved. And so we have to have an additional parameter in there to account for if it's been stretched or compressed, right? You get the idea? I mean, kind of. You don't need to really, I'm just justifying why you need more parameters for a parabola. And as we get even more complicated, like a cubic function that's got 2 bends in it instead of 1 potentially, we need an additional, now we need 4 parameters, and so on and so forth. The more complicated the function, the more parameters we need to specify it. Okay? Questions so far? Comments? No? Okay. The turning point of the parabola is called the vertex, right? So it's going to be, here's the vertex. If the parabola is opening down, what do you think we call it? What would we call that turning point? What is it going to be? It's going to be maximum, yeah, right? Because it's the highest point on the function. If the parabola is opening up, what are we going to call it? Minimum, right? Is this the lowest point? I guess it's right there, right? But that's important. In calculus, this might seem like a crazy thing, but in calculus, a lot of the time that we're going to spend here pretty soon, like about probably 3 weeks coming up right away, we're going to spend doing nothing other than just looking for minima and maxima on functions. That's all we do for a while, is use calculus to be able to find places where the function turns down or turns up, okay? So this is our vertex right here, isn't it? Yes. In this case, it's a maximum. Okay, how would we find the vertex in this case? Well, let's take an example, okay? And we're not even going to worry about graphing this yet. Can you see, though, that if we were able to identify what the axis of symmetry is and what the vertex is, that would really help us graph the parabola, wouldn't it? It would give us a starting place to graph the parabola. So that's what today, by the end of the day, you're going to be able to graph these things just like that. No big deal. But the first step in being able to graph them is we want to be able to identify the important parts of the parabola and put those on the graph. So what's the axis of symmetry and where's the vertex? Okay. Well, you can already tell me, does this one have a minimum or a maximum? Which one? It can be a maximum. Good. How come? Good, because A is negative, isn't it? So it opens down, so it's going to have a maximum, right? Okay? So what are, by the way, what are the values of the parameters a, b, and c? A equals -2, b equals 0, c equals, everybody see that? It's ax squared plus bx plus c. Because the x term is missing, the coefficient must be 0, right? We multiplied it by 0. Okay, so the axis of symmetry, do you remember what the formula was? That's it, negative b over 2a. Okay, so all I've got to do then is plug those values in and see what I get. Well, what's negative 0? 0 divided by, really, who cares? 2 times -2 is -4, but 0 divided by a number is always 0, okay? So the axis of symmetry is just the line x equals 0, right? What about the vertex? What about the vertex? The vertex is always going to be on the axis of symmetry, isn't it? Right? If you think about all these points that are created when I'm folding or reflecting the parabola over its axis of symmetry, like look here, for example. There's a point and there's a point. Those are just reflections of each other, right? Here's another pair of points, there and there. The points that have the same y values, aren't they? Those are going to be reflections of each other. But what about the vertex? What's the reflection of the vertex? Itself, right? The reflection is, it's right on the axis of symmetry, and so it folds onto itself. Okay, so the vertex is on the axis of symmetry. So if I wanted to write the vertex as an ordered pair, well, what's the x-coordinate of the vertex going to be? 0, right? The x-coordinate of the vertex is always going to be given by whatever the x value is for the axis of symmetry, right? So in this case, it's going to be 0. Now, we've done a lot of this earlier in the year, so this kind of brings back some other discussions we had. If I want to calculate the y value for any function that goes with an x value, what do I do?
Look at the comments.
No. I mean, you can find some tricks sometimes, but just in general, what do I do? If I want to find the y value that goes with the x value for a function, plug it in, right? I'm going to evaluate the function at 0, right? So the y value here is always going to be f of x, right? So the y value for the vertex is always going to be f evaluated at -b over 2a, right? So in this case, we're just plugging in 0. So if I go up here to my function, f of 0 just equals -2 times 0 squared plus 7, which is what? 7. So the vertex is at 0, 7. Okay? Let's try another one. Oops, I needed to... So what about this one? Tatum, is that going to have a minimum or a maximum? Minimum, good. And how come?
Because A is positive.
A is positive. Okay, so A is greater than 0, so we have a minimum. What are the values, just everybody, what are the values of A, B, and C? B is, C is, okay. So then what's my formula for the axis of symmetry? Well, the formula is -b over 2a, right?
Yeah.
So then if I plug stuff in, what am I going to get? On the top, I'm going to get 8, positive 8, because I'm doing the opposite of b, divided by 2. 2 times 1 is 2. So 4 is my x-coordinate. So my axis of symmetry is x equals 4. So what are the coordinates of the vertex going to be? 4 something. And to find out, I'll just evaluate the function at 4, right? So the y-coordinate is just going to be f of 4, which is every place I have an x, I'm just going to open up a quantity to dump that value in. So I get a 4 squared minus 8 times 4 plus 9, well, what's that give me? 16 plus 9 is 25, minus 32. 25 minus 32, negative 7. Okay? Good? No big deal. We got this. Okay, so let's do some graphs then. So let's practice some graphs. So what about this guy here then? What's the axis of symmetry going to be here? What are the values of A, B, and C?
A equals negative 3, B equals 0, C equals 0.
Okay. So what can you tell me now? X is going to equal,
Equals 0.
right?
Yep.
So you get negative B over 2A, which is just going to be 0 this time. Okay? So Y then would just equal F of 0. What happens if I plug 0 into my function? I get 0, don't I? Okay. So the coordinates of the vertex then, I'm going to put the vertex right in the middle here. I'm going to put a B for vertex, and my coordinates are going to be 0, 0, right? So I got a point. The vertex is right there, okay? Is this one going to open up or down? It's going to open down. Good. If I want to graph the axis of symmetry, by the way, there it is, right? There's my axis of symmetry. Okay, so now how am I going to get the other points? What could I do? Yeah, I just plug in convenient x values, right? Compatible x values. Well, they're really x values here, compatible x values. What I mean by that is, what if I had a number out front, like say I had negative 3/4 or something? Then I'd want to pick x values, so when I square them, I'd get multiples of 4, so that I wouldn't get fractional answers, if possible, right? But I have a coefficient here that's an integer, so it doesn't matter. We'll just pick ones that surround us. So I could plug in values like, how about relatively small ones, right? Because the graph's going to grow pretty fast. So we could do something like negative 1 for x. If I plug negative 1 in, what am I going to get? So I'm going to get negative 3 times negative 1 squared. What's negative 1 squared? It's 1 times negative 3 is negative 3. And remember, notice what I'm doing here. When we write a vertical t-table like this, that's a convenient way to do it, because then the x and the y columns end up looking like the coordinates of ordered pairs, right? Okay, so I go back 1 and down 3, so there's a point. Well, really I get kind of 2 for 1 there, don't I? I mean, I could do the math, but really if I go over 1 to the right, you can already tell by symmetry, what am I going to get for y? Negative 3, right? So I could have really been smart about that and maybe just done this one first and fill that one in, right? Okay. I would say that for parabolas, it's maybe worth doing 2 points on each side. Really, 2 points, and then you get the reflections for free. So if I went over another 1 to the right of my vertex, and I'm at 2, I'm going to get negative 3 times 2 squared, so negative 12. That's already off the graph, isn't it? Okay, and then if I reflect that up here, I'm going to get positive 2, and I get the same y value because they're reflecting. But either way, I can't even draw the darn thing because it's already off the graph.
That would be negative.
Negative, oh, you're right, negative 2. Yep. Okay. And so if I wanted to graph this thing, I'm just going to do my best estimate of making a parabola. And you just try your best. So it's something, it's just a tall, skinny one that's been flipped over so it's opening down with a vertex at, and let's go ahead and label the vertex, with a vertex at the point 0, 0, right? That's it. Okay, let's try another one. Oh, okay, how about this one? From the graph, what's the domain and range? Okay, domain's going to be all reals, right? Because if I zoom out forever, it's going to go to the left and the right forever.
And the range less than or equal to 0.
Okay, so the range, is gonna be y is less than or equal to 0. Okay, good. Let's try another one of these, and I'm gonna see if you can see some patterns that make it useful in finding the domain and the range. Okay, how about this one? A, B, and C, what are they?
2
1, 2, -8.
plus.
C equals 6, right? Okay, so we want to find the x coordinate of the vertex. So x equals negative b over 2a. Everybody try that on your own real quick. Thank you. Oh, okay.
You got the college.
Yeah.
Something, I don't know.
So what do we get?
2.
2. Good, I'm going to get positive 8 over 4 equals 2. So then y is going to be what I get when I plug 2 into my function. So what's that going to be? What's f of 2? What am I going to get?
No, because -8, yeah.
Right?
But -8 over 4 is -2.
Yeah, but it's not. It's negative b.
Oh,
Right? It's negative b over 2a, so that makes it a positive 8. So what's f of 2? I'm going to get 2 times 2 squared, right? What's that? So that's 8, right?
4
Minus
2 plus 6.
plus 6. So 14 minus 16?
-6.
Negative 2.
Why am I stupid?
So I get the ordered pair then, 2, negative 2. So x is 2, y is negative 2. There's my point. It's opening up. And my axis of symmetry is just going to look like that, right? Okay? And now I'm going to pick some convenient points around that. So what would be a convenient point to pick?
Like 0 or
Okay, so one convenient point would be 0, wouldn't it?
Yeah.
How come 0 is such a good point to pick?
because he's slow.
It's easy to plug in, isn't it, right? If I pick a value 0, plugging in 0 for x means those two terms go away and I get 6. So I get the point 0, 6. Okay, so 0, 6 is going to be 1, 2, 3, 4, 5, 6 right there. Well, I get another one for free, don't I?
Yeah, you get 4.
Yeah, so that's 2 below the vertex, so 2 above would be 4. What's the y coordinate of 4 guaranteed to be? It's got to be 6, right? Because they're reflections. So there's 2 points. And, you know, I mean, that's probably enough. I know a lot of times books will tell you to do 2 points. Now, we can, but you almost don't even need to. If I pick another point like 1, what am I going to get? 2 plus 6 is 8, minus 8 is 0, right? So I get the point 1, 0, so it's right there, which means I also get the point 3, 0, which is right there. You see how I'm getting those, right? Because look at this. How am I getting those numbers so fast? Because this distance, I won't use that, so. This distance right here is 2. Distance, I mean, how far are the x's apart, right? X's are 2 apart here, so they must be 2 apart there, right? These are x values that are 1 away from the vertex. They've got that symmetry, so we have to be the same distance horizontally from the vertex on both sides, okay? And if I graph this thing, what's it look like? It's going to be tall and skinny, opening up. Okay? Get the idea? Now, could anybody tell me, this is like looking way ahead here, so just don't, this isn't something I would expect you to see. But what did the A mean when we were doing our vertex form stuff. Going clear back here. A was but we don't want to think of it as a slope. It's the stretch, right? So we're going to call it the dilation factor. Technically speaking, we would say that this is a value of A, right? That's A, and A is equal to the dilation factor. What's a dilation in geometry?
It's like,
When you're going to zoom in or zoom out, right? So this isn't, we're not dilating the whole function. What we really would call this, and I know this is getting kind of technical, it's the vertical dilation factor, because we're only stretching, we're only zooming in or zooming out vertically, right? We're only growing it or shrinking it vertically. I don't think our book even calls it that, but that's what we'll call it in calculus, for example, okay? The vertical dilation factor. So do you think, I got a question for you. When we picked the value A for standard form, do you think the mathematicians were smart enough to realize, okay, those are going to be the same A's? No, they were. They were smart enough to realize that. So A is the same thing, whether we're using standard form or we're using vertex form. And so A still stands for the vertical dilation factor, right? And so I just want to see if you could come up with, think hard about this one. Could you have come up with an alternate way of maybe finding where those points are on the graph without even using a t-table? So like, for example, if I went 1 to the right,
Relative.
you're gonna go up 2.
why would I go up, the A is equal to 2, right? So the vertical dilation factor is 2. So think what that means. Now I need no talking please, need everybody up here. So the vertical dilation factor is how much I'm stretching that normal distance, the normal y distance from the vertex. So on the parent graph, if I were to graph the parent graph of my absolute value function, think what that would look like. If I'm graphing p of x equals x squared, right? If my vertex, we'll just conveniently put the vertex at the origin. If I go over 1, how far do I go up with an x squared graph? 1. If I go over 2, how far do I go up? Right? And so if I'm going to dilate this thing by a factor of 2, I should be stretching all those vertical distances from the vertex by a factor of 2. So when I go over 1, I'm going to go up how far?
2.
When I go over 2, I'm going to go up
8.
8, right? And so if we look at our graph then, we could have also done that. You see that? We could have said, I'm going to go over 1, but because A is equal to 2, there we go. Because A is equal to 2, I'm going to go up by 2. When I go over 2, instead of going up 4, I'm going to go up by 8 instead. Right? So I could have done this as a dilation instead of using a t-table also. Okay? All right. Good. So try that one. You can do that one. What's the next one? Oh yeah, easy. Try that one. Okay, just because I want to make sure I get through the last example also, I want to pull you together here with me. So did everybody get -1 for your x coordinate? Right, negative b over 2a gives us +1. 2 times -1/2 is -1, so 1 divided by -1 is -1. And if I evaluate the function at -1, I'm going to get -1/2 times 1 minus -1/2 is +1/2. Let's see, yeah. So I got a total of 1/2, right? Everybody agrees, so my coordinates of the vertex are going to be -1, +1/2. So it's not at a very convenient place, it's right there. Here's my axis of symmetry. Okay. Is it going to open up or down? It's going to open down. And so now we want to pick some convenient places to check this thing. Well, what's probably the most convenient x value to plug in? 0. What's f of 0? 0, isn't it? Right? So we know it's going to go through the point 0, 0, which means it's going to go through the point, what other point? -2, 0. There it is. What would be another convenient point to pick? Okay, so we want to, if possible, look, I've got fractions here, right? So it'd be nice to pick an x value that's not going to give me back a fractional answer, so it's easy to plot that point. Okay. Now I got to think a step ahead here. I'm going to be multiplying 1/2 times x squared. So if I plug in something like 1, that's not going to work well because I'm going to get -1/2 times 1. I'm going to get a fraction out of that, right? Okay, but if I pick 2, that's going to be fine because 2 squared is 4, which is divisible by 2. Right? That would be good. 9 or 3 wouldn't work well because I'm going to get 9 over 2. That's going to give me another fraction, right? But 2 is a good one. So if I pick 2, look what happens. If I pick x equals 2, I get the point 2, and that's going to give me -1. Here, let's do it up here. F of 2 equals -1/2 times 4. So -1/2 times 4 minus 2. Did I do that right?
Yes.
2.
It's -4.
Oh, yeah, so I get negative, I don't need the last parentheses. So I get -2 minus 2 is -4. There we go. So 2, -4. So if I go over 2, I go down 1, 2, 3, 4. Which means I've got another point. How far did I go to the right of the vertex there? 3. So I should be able to go back 3 and get to another point. So where's that going to be? Yeah, -4. So I guess stuff right there. Yeah. Well, I didn't exactly space those right. You get the idea. -4, -4. And it's enough for me to graph my parabola, isn't it? Right? That's gonna be hard to draw. So that one's been compressed a little bit, right? Oh, okay, the other thing we wanted to get to. So what about the domain and the range? Let's go back to this last example for a second. So what's the domain of this function? Well, all reals, right? We know that. Oh, darn it. I messed it all up. Okay, that's right there we go, close enough. Okay, the domain was all reals. What's the range?
Y is greater than or equal to
Okay, y is greater than or equal to -2. Well, where's that -2 coming from? The vertex. Good, it's the y coordinate of the vertex always, isn't it? Right? So that's linked to that. Yes?
Is the range just gonna be the opposite, well not the opposite, but of A, like for this
No, it's not. It's not, because I'll prove it to you. So what would have happened, what if when we translated this point, what if it had been like up here somewhere, right? So the vertex had been up here somewhere instead. A is still just the vertical dilation factor, right? See what I'm saying? So the range is not, it's accidental that those are both 2's here, but it's not accidental that it's related to the y coordinate of the vertex. Doesn't that make sense? If this function is a parabola, if it opens down, it's got a maximum, which means it's going to have a maximum y value. All the other y values are going to be less than or equal to that, right? If it opens up, it's got a minimum y value. All the other y values are greater than or equal to that. It works that way every time. So the other thing we could say then is, I keep calling this x and y because I'm calculating x and y coordinates. But specifically, we're talking about the vertex, right? What did we say that the coordinates of the vertex were always called? If we go back to, to our discussion of absolute value functions, we can go all the way back to the very first thing we looked at today, right? We're going to, and once again, we're jumping ahead just a little bit, but you'll be able to make this connection, I know you will. I could have written this generally, right? I could have said any parabola I could write in the form a times x minus what? H squared plus k, right? The fact that that's a squared there now instead of an absolute value just means we have a different parent graph, correct? But the a still means the same thing. It's the vertical dilation factor, and the h and the k are still the coordinates of the vertex, right? So we could kind of jump ahead a little bit because I don't want to get you in a bad habit here. When we write these x's and y's, we really could go back and say, that really isn't an x. It's a specific x. It's h, and that's really k, isn't it? Because we're actually solving for the x and y coordinates of the vertex, and we can specify that by just using h and k, right? So once again, that should really just be a k, and that should be an h, right? If I go all the way back to, I'll change all these so we can see, well, I won't do these, but you get the idea, right? Okay, last one I want to look at. Graphing quadratic inequalities. Man, that looks hard. Is it any harder than what you just did? No, it's not at all. Because if I'm graphing a quadratic inequality, what am I really doing? Instead of, like with a linear inequality, we graphed a boundary line, and then we either shaded above or below, correct? Same thing here. But instead of a line, what's the boundary going to look like? A parabola. In math, we'd say it's a parabolic envelope. Just a fancy word, meaning it's not a line. But it's still going to be a boundary, right? So it's a parabolic boundary. It would be a dashed parabolic boundary, right? And then I'm gonna shade in everything above that. Well, in this case, this parabola opens up, doesn't it?
Yeah.
So it's just going to be the interior of that parabola is going to be shaded because it's everything above the parabola, the parabolic boundary, right? If that were a less than, then I'd be shading everything below the boundary. So like this one, we don't have time to graph it, but let's just pretend that the parabola is right here. I don't know if it really is, right? Because we're shading above, we'd be filling in everything in here forever, right? If we were shading below, we would have shaded everything out there. You get the idea?
Yeah.
Okay. I had to kind of hurry that last little part, but you get the idea. So on Moodle, I'm going to try to build some problems tonight so you can do all this on Moodle. When I have you guys do the quadratic inequalities, here's how you're going to have to do it, and I'll put this in the instructions. If I'm able to get it on Moodle, I can't make a dashed line like this on Moodle. So all I'm going to do is it's going to be a really light boundary line. If it doesn't include the boundary, it'll be a really thick, heavy boundary if it does include. It has the equal sign, so it does include the boundary. Okay?
You guys go to Wilsonville tomorrow?
Yes, early.
Oh, you guys have to stay till Sunday because of varsity.
No, we come back Saturday, but we don't get home till about 3 in the morning. So
So technically it is.
yeah, that's right. Yeah.